We are now going to look at tools to assess a model's fit. What that basically means is that we're going to be looking for observations that are not fit well by the model, meaning that they are not being, let's say, predicted well by the model. We are also going to look at observations that may be influential to the model's fit. What that basically means is that we're going to look for cases where, let's say, an observation is removed from a data set, the model is, let's say, refit, re-estimated, and the model greatly changes. We want to identify those observations where that can occur. And so that's the purpose of section 5.2 of my book, is to basically look for those two different things. Now, when my co-author and I sat down to write this particular section, our goal was to try to unify the models of Chapter 2, Chapter 3, and Chapter 4 into this assessing a model's fit. Early on, we found out that it would be very difficult to include the models of Chapter 3 in this discussion for a number of different reasons. First of all, the tools in R are not as much available as they are for the Chapters 2 and 4 models. And also, even the statistical development behind assessing the fit of a Chapter 3 model is not as well developed. So then that left us to try to unify the discussion relative to Chapters 2 and 4. As we were going along, we found, again, there are a number of differences between the models where, well, we cannot talk about everything at the same time, but we will periodically need to say, okay, for Chapter 2, we're going to need to deal with this issue. For Chapter 4, we're going to need to deal with this issue. And so in the end, I think we're satisfied with how we approached the discussion, but it's just helpful, I think, for my students, readers of my book, to know that how we came about with this approach. Okay. So the first difference between, let's say, looking at these assessments of model fit for Chapters 2 and Chapters 4 deal with an issue with regards to Chapter 2 in terms of how we handle the corresponding data that we would have for a logistic regression model. So we're going to talk about something that we refer to as explanatory variable pattern form. And so in our data frame that we've seen for the place-kicking data set, we have our response variable good, which is a 1 if the kick is a success, a 0 otherwise. This is referred to as, let's say, the Bernoulli response format for our data. We have a 1, we have a 0 for our response. Now, when we have data like this, what we like to be able to do is transform it into an explanatory variable pattern form. What that basically means is that we're going to reconstruct our data into a binomial format. So for each unique set of explanatory variable values, we're going to find the number of successes, we're going to find the number of trials, and now look at the data from a binomial point of view. We've already actually done this in the past. Well, I just didn't call it explanatory variable pattern form, or EVP form. And back in Chapter 2, when we only had distance as our explanatory variable, what we did was we found the number of successes at each unique distance, found the number of trials at each unique distance, and we summarized the data like this. So for example, at 18 yards, there was 2 successes out of 3 trials. At 21 yards, there were 19 successes out of 20 yards. Now, if we were to reconsider this data set also with, let's say, the change variable as well, then what one would do is you might have a situation where, well, you would, let's say, add another column here, call it change, and for 18 yards, we might have 0 or 1. 0 for not a lead change kick, 1 for a lead change kick. We look at the number of successes for the case of distance 18, change 0 out of a certain number of trials. Then also we look at the number of successes out of a certain number of trials for distance of 18, change equal 1. Then we would go to 19 yards. Again, we would look at the two cases, 0 and 1. And so what we have here then in every row of our data frame is a unique set of explanatory variable values. And again, we look at the number of successes out of a certain number of trials. Okay. Well, why do we want to basically transform the data to this EVP form? Well, the reason is because many of our statistical measures that we're going to use to evaluate how well a model fits our data are based upon continuous distribution approximations. Now, we know that when we look at the number of successes and number of trials, that fits a binomial. But our measures to assess how well our data is being fit by the model are based upon continuous distributions, such as the normal, such as the chi-square distribution. And by working with the binomial format, we will more likely be able to get a good approximation than if we were to stick with just a Bernoulli format. You'll see some examples of that that make it quite clear shortly. Okay, so let's talk about residuals. All of you should have seen residuals before this class in the context of a normal linear regression model. And so what we're going to do here is extend these same ideas now to the Chapter 2 and the Chapter 4 models. Now, when you learned about residuals in the past, basically you did this. You took your observed values minus the corresponding estimated value for that particular observation. So in a very general sense, for normal linear regression models, you might have a y as your response, and then you would have y hat as your estimated value from your model. And that's how you would form a residual. Now, for our particular case here, we're going to let W denote the observed count that we have. So W could be the number of successes out of a certain number of trials, or W could be the count for our Poisson regression case. Now, for our Chapter 2 models, what that means is our residual is as follows. You take the observed count minus the estimated count based upon your model. So N would be the number of trials for a particular EVP times pi hat, which would be the estimated probability of success. Now, with respect to our Chapter 4 models, we can see that we have a little bit of a notation change then here with W. W is going to be our count. So it could be, let's say, the number of horseshoe crabs for a particular situation. And its corresponding estimated value from our model is mu hat. That's our residual. So for example, if we go back to the place kicking data set at 21 yards, if you remember, we had 20 trials and we had 19 successes. So W was 19, N was 20. If you go to your model itself, the estimated probability of success for that situation is 0.9676. So in the end, my residual is negative 0.35. So we can see that the model is predicting a little bit higher estimated number of successes than what was actually observed. Okay. Now, to help with the notation, so we could talk about Chapter 2 and Chapter 4 models together at the same time as much as possible, we're going to do a little bit of a notation change here. This estimated count from the Chapter 2 models, I'm just simply going to call it W hat. The estimated count from the Chapter 4 models, rather than using mu hat, I'm going to call it W hat as well. So then our residual becomes W minus W hat. Also, to help us deal with this little bit of a different notation, rather than, let's say, having let's say n observations across the entire data set. Notice how that causes a little bit of a conflict with our notation in terms of the number of trials for a particular EVP. Rather than using n, we're going to say that we have capital M observations. So relative to that place-kicking data set, when we only look at distance for the explanatory variable, we would have capital M different unique distances in our data set. So that in the end, if I want to talk about, let's say, a particular, observation for our data set, W sub M is going to be the observed count for the mth observation. W hat sub M is going to be the estimated count for the mth observation based upon our model, like a logistic or Poisson regression model. For the chapter 2 models, then there are going to be N sub M Bernoulli responses or trials for each row of our data frame, such as 20 observations at a distance of 21 yards. So now with this notation then, we can look at these residuals in a little bit better manner. You know, the problem with only looking at Wm minus W hat sub M is that it doesn't tell us if, you know, it doesn't take into let me restate this. It doesn't really give you information about, well, what is, let's say, unusual in size. You know, again, at the very beginning of these notes, I talked about how we want to find, let's say, particular observations that are not fit well by the data. In those kinds of settings, we often refer to these particular situations as outliers. We want to find outliers. Excuse me. And so what we need to do to find an outlier, we need to take into account the normal, let's say, variability that you would have in your data to say, you know, what is a large residual relative to your situation in terms of your sample size, in terms of your model. And to do that, what we're going to do is first begin with talking about something called a Pearson residual. So rather than only looking at Wm minus W hat sub M, we're going to also now divide by the square root of the estimated variance of the random variable W sub M. We're going to refer to this Pearson residual as E sub M, E for error. Now, for a logistic regression model, or for actually any of the models in Chapter 2, what that means is that that variance, that estimated variance, is simply the regular old variance that you would have from a binomial, except for I'm going to put a hat on top of the pi to allow me to put in the estimated value. Now for a Poisson regression model, we know that the variance of a Poisson random variable is simply mu itself, if we think of our regular notation that we had before. So what that means then for us, that the estimated variance, again the estimated variance, would be W hat sub M. So if we look at this in terms of the place-kicking data set, where we have again a distance of 21 yards, we had 20 trials, 19 successes, we could find now the Pearson residual as follows. W sub M minus W hat sub M divided by the square root of that estimated variance from a binomial, and we get negative 0.4449. Now, what can we do with this? Well, these Pearson residuals can be somewhat approximated by a standard normal random variable. So, you know, back in your very first stat course, you learned about a standard normal distribution. It looks something like this. And we learned that, let me just write this out here, about 99% of the time, you should be between about negative 2.56 and positive 2.56. Well, just in our notation that we've seen before, this would be corresponding to Z sub 0.995, Z sub 0.005. And so anything outside that range, let's say if I have a value of, let's say, positive 4 or negative 4 for relative to the standard normal, if you had that kind of a value, you would think, okay, that's kind of unusual. And so we use that same kind of logic then with these Pearson residuals. In this particular case, I have a value of negative 0.4449, so I'm right about there. And so having a Pearson residual like this would not be unusual. And so I would not say that this is outlier. I would say that this particular observation seems to be relatively fit well by the model. Now, with these Pearson residuals, there's one little problem with them. And in the end, we don't often use Pearson residuals because we want to fix this problem that I'm going to talk about here. And the problem is that we could think of what's in the numerator as I have a random variable here. And of course, in this W hat is an estimated value. Now, I'm thinking of these in terms of random variables. So I know I have a little w there. That means the observed value. But think of it in terms of random variables for a moment. So I have two random variables that I have here in my numerator. And I would like to take into account the variability for both of them. So rather than dividing by the estimated variance of w sub m, how about we divide by the estimated variance of w sub m minus w hat sub m. And when I do that, I have what's referred to as now a standardized Pearson residual. And the end result is that this will be this will be better approximated by a standard normal distribution than if we were just to use the Pearson residual alone. Now we're going to call this standardized Pearson residual R sub m, R for residual. I guess you could make it a little bit more descriptive, but this is very common notation that people use, so we're going to use R here. And what ends up happening is that basically in this denominator you have that same variance that you had before, but now you multiply it by 1 minus this quantity called h sub m. Now this h sub m is a little bit difficult to explain without matrix algebra. So in terms of, for students who are taking my course, you're only expected to understand the corresponding computation of it and that this h sub m exists. For those who are, let's say, reading my book and want a little bit more of a detailed explanation about it, you can take a look at the book, and I'm going to give a little bit more detail here as well. Especially for those of you who've had a full semester of a normal linear regression, you've come across this h sub m before, and it's basically the same thing. So the next part here is not for students who are taking my course. They're not expected to necessarily understand this unless for some reason in a particular semester I decide to focus on it in more detail. You will know if that occurs. Okay, so enough about that. So this h sub m comes from what's called a hat matrix. In a normal linear regression setting, for those of you who've taken a course on it, you've learned about something like this, where y is a vector of the y is a vector of the corresponding response values in your data set, and this h is a matrix. And what h does, when you take h times y, it essentially in the end finds your estimated values for y, or your y hats, and because of that, h essentially puts the hat on top of y, and so that's where the name hat matrix comes from. How is the hat matrix found? Well, let's let x be a matrix of the explanatory variable of values, where the first column is a column of ones, and then each column after that is the corresponding variable values for each variable of interest. We're going to create a matrix called V hat, which has the diagonal elements of the estimated variances for W hat. And then if I were to do this matrix algebra operation here, this is how you would get the hat matrix. And all this hat matrix, where all this comes from is its representation in what's called a weighted least squares situation. Again, this is extra material that students for most semesters in my course would not be expected to know, but it's good to briefly talk about here, especially for those of you who've had some additional background. Okay. Now, since this standardized Pearson residual can now be approximated by a standard normal distribution, what we do with it is similar to what I mentioned with the Pearson residuals. We calculate, let's say, the standardized Pearson residual for each observation or each row of my data frame, and I compare it to what I would expect for a standard normal distribution. So roughly speaking, if I have values of my standardized Pearson residual outside of plus or minus 2.56, then I might be worried about that perhaps the model is not being fit well by my data. And that's actually how you would approach this in a very similar manner for normal linear regression. With the models that we are talking about, especially the logistic regression models, one cannot rely on this approximation to always work. And this unfortunately makes the whole concept of model assessment much more difficult, especially for logistic regression models. Here's an example to help explain this. So, what we are basically doing is making a normal distribution approximation for a binomial random variable. Because, in the numerator for our standardized Pearson residuals, we have this W sub n. It's a discrete value, 0, 1, 2, all the way up to n. And then essentially has a binomial distribution. But what we're trying to do in the end is try to actually approximate the distribution with a normal. Sometimes it can work, other times it definitely does not. Here's an example of this. So let's say we have a situation where pi hat is 0.9. So we have a situation where the model says it's likely to have a success. We observe one success out of only 3 trials. So not very many trials at all. Now notice in this particular situation, the W was observed to be 1. But in the end, it could have only been 4 possible different values. 0, 1, 2, and 3. So a very discrete set of outcomes that one could have. And again, what we're going to try to do is use a normal distribution approximation to approximate probabilities associated with this W. If we just look at the Pearson residual, because it's just easier to work with here, because we don't have to work with the hat matrix value. My Pearson residual is negative 3.27. And when you see that, you might be thinking, uh-oh, we might have a problem here. This is outside, if I were to use a strict standard normal approximation, it's outside of the negative 2.56 range, or negative 2.56 to positive 2.56. And here I have an observation that's not being fit well by the data. In the end, that's actually incorrect to think that in this situation. Here's why. So what one can do, and you can look at some of the details here on your own. I'll briefly talk about it. How about we look at probabilities associated with this Pearson residual? And I created an object called W, which allows me to put in the possible values, 0, 1, 2, and 3. Put in an object called N. It's 3. There's my pi hat. Then I find the Pearson residual for each possible value of W. And so in the end, and you'll see this when we put all this together, here's that negative 3.27 that we get for W at 1. Next, how about I do this standard normal distribution approximation with this? And so what I'm going to do is, let's say I have a random variable, let's say Z has a standard normal. What I'm going to do is look at the probability that Z is less than negative 3.27. This gives me a measurement of how extreme negative 3.27 would be relative to a standard normal distribution. And so to do that, or if I did that, then the probability is extremely small, 0.0005. But we know here that this Pearson residual can only have one of four values. And we actually know that we can estimate then the corresponding probabilities of being each of those values using our binomial distribution. So instead, how about I look at something like this? How about we let capital E be, let's say, a random variable version of what the little e represents. And I want the probability that E is less than negative 3.27. Well, I know what that is, and I can find that, or I can estimate it, I should say, from using that binomial distribution. So how do I do that? I can use the p-binom function. This gives me probabilities of just for a regular binomial. Let's say probability W is less than or equal to 1. It can give me that probability where I put in the number of trials of 3. And I don't know what pi is, but how about we just put in the corresponding estimate from the model? So whatever the pi hat would be, which is 0.9 in this particular case. That particular probability is 0.028. And so we can see there is a difference there from what the normal distribution gives us versus what the binomial distribution gives us. Now it's more likely to have a situation where you have negative 3.27 versus if I were to use the standard normal distribution. And we can use the same kind of approximation, let's say, for W equal to 2. Find the Pearson residual. Standard normal approximation, I get a probability of being to the left of it, about 0.09. But with that binomial, it's 0.271. It's a reasonable thing to have happen. And we can look at then the last case too. We see differences amongst those probabilities. So the whole purpose of this perhaps long discussion here is to show you that when we use a normal distribution approximation, those corresponding probabilities are often different from our best estimate of what the actual probability is when we use the binomial distribution. And so we have to be very, very careful with saying something is an outlier relative to these Pearson, relative to these standardized Pearson residuals. When we have to be careful, corresponds to when n is very small, meaning that we don't have a whole lot of different possibilities for what the actual residual could be. But there's actually another situation where we have to worry about that. So let's say that I have n sub m be 100. So I have 100 trials at a particular, related to the place kicking data set, I have 100 trials at a particular distance. Now you might be thinking, okay, now I know that the W and then the corresponding E or the R is going to have 101 different possible values. So the normal distribution approximation should work well. In the end, it will not if pi hat is very large or very small. Because what this is saying is that almost all the probability is going to be is going to correspond to situations where you have a large number of successes, and you're going to have a very, very low probability of having, let's say, W equals 0 or W equal 1. And so in the end, while there are a lot of possibilities for W, most of them are very improbable. And so almost all your probability is going to be on just a few cases here. And so now this standard normal distribution approximation, unfortunately, is not going to work as well here. Okay, we will, in another set of notes here, have some nice plots to help demonstrate some of this stuff too, because I can understand that this might be a little bit difficult to comprehend at first. Now, with the Chapter 4 models, we don't necessarily have the same difficulties. The only time that you ever have to worry about this is, let's say, when W hat sub m ends up being very small. And then you might be worrying about if that normal distribution approximation is going to work for a standardized Pearson residual. So in the end, what one should do is use, let's say, some rough guidelines for when one may be concerned about a particular observation not being fit well by the data. Typically what I do is I use guidelines of plus or minus 3 with each of my observations. If I have a particular observation that has a standardized Pearson residual outside that range, then I make note of it and think about, okay, maybe this observation is not being fit well by my data. But rather than concluding, uh-oh, the model doesn't work, what I'm going to conclude is, okay, let's make note of this, and we're going to come back and investigate this further later to see if maybe we can determine why this is occurring. The why could be simply the normal distribution approximation is not going to work for some of the reasons that I mentioned earlier. Okay. Now, typically one should always work with standardized Pearson residuals rather than Pearson residuals. Why did I introduce Pearson residuals? Well, it just is a nice way to get to the standardized Pearson residual part. And there can be, let's say, more complicated models outside of this class that you might run into where the standardized Pearson residuals are very difficult to calculate. Also, outside of this class, you might see people actually use just the Pearson residuals alone. So that's why it's good to know what they are. Here's a interesting situation. Suppose you expect that the n sub m's for the chapter 2 models are all going to be approximately 1. So essentially, you're going to have Bernoulli data. And there's no way that you can, let's say, aggregate your data over, let's say, the unique combinations of the explanatory variables to find the number of successes out of the number of trials, where if you do that, in the end, basically everything's unique. There's only going to be one trial. So, well, when would this occur? This is going to occur in a situation where you have, let's say, an explanatory variable that is essentially continuous. In a continuous variable situation, you're not going to have duplicates of their particular values. And so, in the end, you are only going to have a situation where everything is unique. Relative to the place-kicking data set, one place where that kind of happens is, let's say, if I only were to use the time elapsed variable in my data set, that's a situation where, since there are so many unique times in that data frame, it's going to be hard to have many n sub m's be, let's say, greater than 2 or 3. Now, and then in the end, this is a very good question. How does this affect the use of then the Pearson residuals or standardized Pearson residuals? Well, in those particular cases, standard normal distribution approximation is just not going to work. It just isn't. And that, unfortunately, then leaves us a tool, removes a tool that we can use to assess how well a model fits the data. Now, there are other types of residuals out there. In particular, you're going to see something called a deviance residual. I don't typically talk about these very much in our class or in a course or in my book, because they give you basically the same information as a Pearson residual does. However, sometimes people will use these, and so it's good to at least briefly know what they are. Okay. So the deviance residual is based upon something called a residual deviance. We've talked about the residual deviance before. It's a negative 2 log lambda statistic that allows you to test, let's say, your model of interest versus a saturated model. If you were to look at the actual mathematical expression with it, you can always write it in this term, or write it like this, where I sum over the observations in my data set, and for each observation in my data set, I will have a particular value for it. And when I sum them all together, I get the residual deviance. Take a look back, for example, at chapter 2, how the residual deviance was written. Now, since I can always write my residual deviance in that way, so that every observation contributes one particular value in that sum, then how about we just simply look at each of those values for a residual? And that's what a deviance residual does. In the end, one square roots it, and then one attaches a positive or negative sign to it corresponding to the difference between W and W hat. So if W was greater than W hat, I put a plus out there as the sign. If W is less than W hat, then I put a negative out there as the sign. So using this relationship then, if I call my deviance residuals E sub m and then a superscript d for deviance, if I were just to simply square those and add them all up, then I get that residual deviance back. The standardized deviance residual ends up being exactly the same, except for now I divide by the square root of 1 minus the hat matrix diagonal value. So how do I actually do some of these calculations then in R? We're not simply going to be programming in these expressions that I've given you. R has some nice functions that automatically do this for us. The residuals function in R, if you put an argument of type equal Pearson, it will give you the Pearson residual. R standard with a type equal Pearson gives you the standardized Pearson residual. Okay, so that gives you some information about Pearson residuals, standardized Pearson residuals, how to examine them, and how it can be very difficult to examine them to determine if your models fit well by the data or not. In the next set of notes, we'll actually take a look at some examples to explore this further.